Hello and welcome. Today, we're pulling back the curtain on one of medicine's most incredible breakthroughs, the X-ray. We're going to follow the journey of a single invisible photon of light, from its violent creation inside a machine, through the human body, and on to the final image that can literally save a life.
And you know, it all started completely by accident. A physicist named Wilhelm Roentgen was messing around with cathode rays when he noticed this strange, mysterious glow on a screen nearby. He had no idea what these new rays were, so he just called them X, for unknown. And this right here, was the very first image he took, of his wife Anna's hand. It absolutely stunned the world, revealing the bones inside a living person. Just like that, medicine was changed forever.
So, what exactly was this revolutionary light that Roentgen stumbled upon? To really get why it has the power to see right through us, we first have to understand what it even is.
Okay, so X-rays are part of the same big family as the light we see every day and even the radio waves that carry our music. It's all just electromagnetic radiation. The real difference, the secret sauce, is energy. X-rays just pack a way bigger punch. Their wavelengths are so incredibly short that they can zip straight through soft stuff like skin and muscle, but they get stopped in their tracks by denser materials, like our bones.
That high energy is everything. But you can't create X-rays by just, flipping a switch like you would for a light bulb. Oh no. It takes a very specific and surprisingly powerful process. So, let's dive into how it's done.
This right here is the heart of the whole operation, the X-ray tube. Honestly, you can think of it as a highly controlled photon cannon. On one side, you've got a negative cathode, which is our electron source. On the other, a positive anode, which is our target. All of this is sealed inside a vacuum, and it's all powered by a massive voltage supply.
Now, the process for creating an X-ray is, well, it's surprisingly violent. First, we heat up a tiny filament until it literally boils a cloud of electrons right off of it. Then, a huge voltage difference yanks those electrons across the vacuum, accelerating them to almost the speed of light. They slam into a tungsten target with so much energy that over 99% of it is just wasted as pure heat. It's that tiny leftover fraction, less than 1%, that actually gets converted into the X-ray photons we need.
So during that incredible collision, two main things can happen. The first is called Bremsstrahlung, which is German for braking radiation. A good way to think about it is like a speeding car that has to swerve hard to avoid hitting something. It screeches its tires, right? That screech has lost energy. Here, the electron swerves around an atom's nucleus, and the screech is an X-ray photon. This makes a really broad mix of different energy levels. The other method is called characteristic radiation. This one's a lot cleaner, more like a perfect shot in pool. The incoming electron smacks an inner electron right out of its orbit, leaving a hole. When another electron drops down to fill that spot, it releases an X-ray with a very specific predictable energy. It's a signature move, unique to that target material.
Alright, so our beam of invisible photons has been created. Now for the magic. What happens when this beam actually travels into the human body? This is where the image really starts to take shape.
The most important interaction is called the photoelectric effect. Here's what happens. When a relatively low-energy X-ray photon hits a dense atom, like the calcium in your bones, it gets completely absorbed. Poof, gone. The photon gives up all its energy, knocks an electron out of the way, and just vanishes. And because it never reaches the detector on the other side, it leaves a blank spot, a shadow. On the final X-ray image, that shadow is what shows up as bright white. This is exactly why bones are so clear.
But not every photon gets absorbed like that. Some of them, especially in our less dense soft tissues, just kind of glance off an electron. This is called Compton scattering. The photon loses a little bit of its energy and just ricochets off in some random new direction. Now, these scattered photons, they are the enemy of a clear picture. They hit the detector from all these weird angles, creating a kind of gray fog that just degrades the contrast and sharpness of the final image.
So, what you're seeing in the end isn't really a photograph, it's a shadowgram. It's basically just a map of what got through and what didn't. The bright white parts are the deepest shadows, where photons were completely stopped by bone. And the grays and blacks, that's where photons either zipped right through soft tissue or got scattered on their way to the detector. So we have this raw shadow play. How do we turn that into a crisp, clear, diagnostic image that a doctor can actually use? Well, as it turns out, it's a very delicate balancing act.
Radiographers and medical physicists are basically master jugglers. They're constantly trying to balance these four things: enough contrast to tell tissues apart, high enough resolution to see tiny details,
low enough noise so the image isn't all grainy, and enough sharpness to make out clear edges.
And one of the biggest dials they can turn is the tube voltage, or kVp. This controls the energy of the X-ray photons, and it's a perfect example of a constant trade-off. Just look at the two images here. A lower kVp on the left gives you this beautiful, high-contrast image with stark blacks and whites. But the photon got weaker, so you need more of them, which means a higher radiation dose to the patient. A higher kVp on the right penetrates better and lowers the dose, but you lose a lot of that beautiful contrast. Finding that perfect sweet spot is the real art and science of this job.
And that brings us to the central challenge of all of this. These photons are powerful enough to see inside of us, right? Well, that also means they're a form of ionizing radiation, and that comes with an inherent risk that has to be managed really, really carefully.
The entire world of radiation protection is built on this one simple but profound philosophy: ALARA, as low as reasonably achievable. It just means you never, ever use more radiation than is absolutely necessary to get a good diagnostic image. Every single decision is guided by this principle.
So how do you actually achieve ALARA? Well, it comes down to three fundamental tools. First, time. Keep the exposure as short as possible. Second, distance. Get as far away from the source as you can. Radiation intensity drops off like crazy the farther you are. And finally, shielding. Use materials like lead that absorb the radiation. This is why you see medical staff wearing lead aprons and standing behind protective walls.
But it is so important to put this risk into perspective. Have a look at this table. A standard chest X-ray gives you a dose that's equivalent to about 10 days of just living on planet Earth from the natural background radiation all around us. Even a much more powerful CT scan is only about 3 years' worth. When you weigh that tiny risk against the life-saving information these scans can provide, the benefit almost always wins hands down.
So, let's recap our photon's incredible journey. It was born in a violent collision inside an X-ray tube. It flew through a human body, creating a shadowgram based on whether it was absorbed or just scattered. That shadow was then carefully tuned to create the clearest possible image, all while being guided by that fundamental principle of patient safety, ALARA.
And what's really amazing is that these fundamental principles aren't just history. They are the absolute bedrock of even more advanced technologies. A modern CT scanner? It's essentially a really sophisticated X-ray tube and detector spinning super fast around a patient, taking hundreds of these shadowgrams that a computer then stitches together into a stunning 3D image.
And all of this leaves us with a final thought. The physics that Roentgen discovered over 100 years ago has given us this incredible, almost magical power. But as our technology gets even better, letting us see with more and more detail, that central challenge remains exactly the same. How do we balance our quest for the perfect image with our absolute duty to protect the patient?